Welcome. In today's lesson, you're going to be set research on evidence for special relativity. As a result, as part of the lesson, you're going to fill out this document that you'll find at the bottom of the classroom. Just quickly to run you through what you're going to do, the syllabus dot point says that you have to supply evidence in 3 different categories. So what you're going to do firstly is outline very briefly, please don't spend a lot of time here. These are the Einstein's thought experiment for time dilation. That's one which has the mirrors going up and down as the object is moving sideways. This is the Einstein's thought contraction. This is the train or the bus where it's moving sideways and the mirrors are at one end. Okay. You then have to make a statement about why experiments why thought experiments are not considered evidence for special relativity. In science, as you know, physics especially, intuition is often not correct. We need evidence, physical evidence. And as a result, we had no evidence for special relativity for a very long time because the instruments that we needed to make the measurements of masses and velocities and lengths and so on back in 1905 weren't around. So it took us quite a while to come up with the first levels of evidence that started to support special relativity. And remember, we need 3 levels. We need to prove but have evidence for time dilation, length contraction, and relativistic momentum. So the syllabus outlines 3 things that we need to be able to do. Okay, so I've included in the link on Classroom the videos that go along with this, as well as your own research. The first, you have to first bit of evidence that you're going to be using is the observations about the muons entering the Earth's atmosphere. We're able now to measure the decay rates of muons, and we know that muons which are traveling at fast velocities take longer to decay than muons that are stationary in the laboratory. So that is the first part of the evidence. So you need to describe how each of these how this is evidence for special relativity. Please make sure that in your response you do include when this was first done, because it's part of this part up here to explain why it took a while for special relativity to be supported by evidence. So it's just that you need to know that it was maybe back in the 1960s or so on. So that's the first of the evidences that is mentioned in the syllabus. The second is the famous Havlik-Keating experiment, or the atomic clock experiment, where atomic clocks were synchronized and then sent on airplanes going with and against the rotation of the Earth. And so there's a video which is in the link for you to go there. Once again, if you could please include in your description of the experiment at least the approximate time, that year that this was attempted. You don't need to memorize exact years. You're not doing a history assessment here. It's just simply you need approximately the decade. Once again, referring to the whole idea is Einstein published special relativity back in 1905 with his 2 postulates. The actual name of that document is on the electrodynamics of moving bodies, and it took us a while to be able to have the technology to do so. Third piece of evidence is the accelerators. As part of the worksheets that you have been completing, one of the worksheet questions was as we accelerate protons and electrons to near speeds of light in Large Hadron Colliders and other accelerators, we need to adjust electric and magnetic fields to take into account relativistic momentum. So, or in some places, people would like to call that relativistic mass effect. Okay, so you will, if you go back to the to that problem, you may even use that as an example. Okay. The in doing that one with the accelerator, please use these equations there. Remember, F equals QVB is the magnetic force, and this is the centripetal force here. You should be able to use these as evidence as how we would derive the formula for the magnetic field strength. Okay. And finally, a really interesting one that is added to our syllabus, which is, I'll just get you the actual reference. This is our syllabus here. You can see there are 4 things that we need to make sure: cosmic origin of muons, the Haffler heating experiment, particle accelerators. This one here is in, I'm trying to find what it actually means in different textbooks. In most textbooks, nearly in every textbook, it's just glanced over because I don't think the writers of the syllabus really knew what they were asking here. So what I think that dot point is actually asking is this one here. It's stellar aberration. So if you could go to stellar aberration, basically on Wikipedia, and work out what it means, when light enters through our atmosphere, it comes in a straight line. But if we're moving into that light, it will look like it's moving at a greater angle towards us. And this greater angle is called stellar aberration. You might want to do a little bit more research than just the Wikipedia, of course. There's some great pictures there about the fellow who did it. So in your response, briefly outline what is meant by stellar aberration and how it only makes sense if we use special relativity. Okay. I've given you at the bottom of this document a whole series of other hyperlinks that you might want to use, as well as links that are on the classroom page. Okay. Thanks very much.